Let's look at a program that interfaces a stepper motor with 8051. Before going into the details of the program, let's see how a stepper motor works. It works on the principle of electromagnetism. Like any motor, it has a rotor and a stator. The rotor is soft iron or magnetic, and the stators are made of electromagnets, and the electromagnets are energized in a sequence so that the stepper motor turns clockwise or anti-clockwise. And the name stepper motor comes because it rotates in steps. Suppose the stepper motor has a step angle of 2 degrees, then it will rotate 2 degrees, stop, again rotate 2 degrees, stop, and so on. The motion is not continuous, but it is in steps. That's why the stepper motor is called so. Now let's see how the electromagnets need to be energized so that the rotor will turn clockwise. So let's look at the windings first. You can see that X bar is a single winding and it has a center tap which is connected to logic 1. Similarly, Y bar is a single coil whose center tap is also connected to logic 1. So X and X bar, they are complements. If X is equal to 1, X bar will be 0. And if Y is equal to 1, Y bar will be 0. So now let's look at the first sequence that has been sent to the windings. X is equal to 0, Y equal to 0, and therefore X bar equal to 1, Y bar equal to 1. Now look at the rightmost figure. You can see that X, Y, X bar, Y bar. This is the clockwise direction. These windings are arranged in the clockwise direction in this order. X, Y, X bar, Y bar. And if you look at the middle diagram, you can see that the center tap is at logic 1, that is plus 5 volt. So if the other end of the winding is at logic 5, there will be no current flow. And if it is ground, there will be current flow. So now let's look at the pattern. X and Y are zeros. So this is plus 5, X is 0. There is a potential difference and there will be a current flow. So this winding or this electromagnet will be energized. So you can see it is shown in red. X has been energized. Similarly, Y is equal to 0. Center tap is at plus 5 volt. There will be a current flow through the coil Y. And therefore, this magnet will also be energized. And since these two magnets are energized, the rotor will occupy a position in the middle of these two stators. X bar and Y bar meanwhile are at logic 1. That is, the voltage at X bar is plus 5 and at the center tap is also plus 5. Therefore, there is no potential difference and there is no current flow. Therefore, X bar is de-energized. Similarly, Y bar is also de-energized. Thus, the magnet, that is the rotor, will occupy a position between X and Y as shown in the figure. Now, if we have to rotate the rotor clockwise, we have to energize X bar and Y next. The sequence required for that will be X equal to 1, Y equal to 0, X bar equal to 0, Y bar equal to 1. Now let's see what happens when this sequence is applied to the windings. When X is equal to 1, the common point and X both are at the plus 5 volt and there will be no current flow. So X is de-energized. Y is 0. Therefore, there will be current flow between the common point and Y. So the coil Y will be energized. Y is energized. Again, X bar is equal to 0. Therefore, there will be a current flow between the common and X bar. This electromagnet will be energized. X bar will be energized. And if you look at Y bar, it is at logic 5. Common is at logic 5. There will be no current flow, and correspondingly Y bar will be de-energized. So now X bar and Y are energized and Y bar and X are de-energized. So the magnet will now shift or rotate clockwise such that it occupies a position between X bar and Y. Now, if we have to rotate the rotor clockwise, we have to energize X bar and Y bar. The sequence for that will be 1100. Now, when this pattern is applied, X bar and Y bar will be energized and the rotor will rotate clockwise such that it occupies a position between X bar and Y bar. Now, if we have to rotate this rotor clockwise again, we have to energize Y bar and X next, and the pattern for that will be 0110. So now Y bar and X will be energized and the rotor again turns clockwise another step. So this is how the rotor will rotate when you apply the sequence 3, 9, 12, 6, 3, 9, 12, 6 in that order. Now suppose you have to rotate the rotor anti-clockwise. What should you do? You should apply the same sequence in the reverse order. That is, you should apply it such that 6, 12, 9, 3, 6, 12, 9, 3. This sequence appears at the coils. So if you reverse the order, the rotor will rotate anti-clockwise. Now let's look at the interfacing diagram. This is very important. If a question is asked, this diagram will carry up to 4 marks out of 10. In this diagram, you can see that the port pins of 8051 is not connected to the windings of the stepper motor directly. There is an IC in between, the ULN2003. This IC has been placed because 8051 cannot provide enough current to the stepper motor so that the coils can be energized and the motor can turn. This current has to be supplied using an external IC, the ULN2003. It is a driver IC that supplies enough current to the device connected at its output. So you can see that 4 port pins of 8051 are connected at the input of ULN2003, which inverts the signal, and the output of ULN2003 is applied to the 4 windings of the stepper motor. The common points or the center taps of the windings of the stepper motor are connected to plus 5 volt. That is logic 1. And you can see that the values at the port pins are inverted by ULN2003. And when we discussed the working of the stepper motor earlier, we discussed it considering the values at the windings, that is X, Y, X bar, Y bar was the output at the ULN2003. This is directly connected to the stepper motor windings. We discussed this sequence. And since this is the inverted sequence, the value at the port pins should be the complement of this. That is, here at the input of ULN, the sequence will be X bar, Y bar, X, Y. So look at the last sentence, that is very important. To energize a particular stator pole, a high should be sent to the port pin connected to it. That is, suppose you have to energize the winding X, then you should send a logic 0 at the port pin. That is, if you have to energize X, you should send high here. It will be inverted here. You will get a 0 here. And if this is 0 and look at the sender tap, it is at plus 5 volt. So here it will be plus 5 volt and here it will be 0. So there is a potential difference and there will be a current flow, and this particular coil will be energized. So to energize a particular stator pole, you should send a high to the port pin which is connected to that particular winding. So that will be the pattern that we need to output through 8051 when we connect or try to program a stepper motor using 8051. Now look at the sequences that has to be sent out through 8051's port pins. This sequence is called the normal 4-step sequence. That is what we discussed earlier. In this case, at a time, 2 coils will be energized and 2 coils will be de-energized, and the rotor will occupy a position in between 2 coils. So you can see that the pattern is as shown. The same values are repeated here. And you can see that when you give the sequence in this order, that is 9, 12, 6, 3. If you give the sequence in this order, the stepper motor will turn clockwise, and if you reverse the order, it will turn counterclockwise. So this table shows the values that are to be sent to 8051's port pins. Now the effect of sending this sequence to the stepper motor is as shown. You can see that the rotor occupies a position in between the stator coils. So this is known as the normal 4-step sequence. Now there's another sequence called the wave drive sequence, where you energize only one coil. So the pattern to be sent out through the port pins is as shown. So there is a single one and all others are zeros. When this is complemented, you will get a single 0 and all other will be 1. That pattern will appear at the input coils of the stepper motor, and the effect is as shown. Only one coil will be energized and the rotor will be aligned parallel to the stator. Again, the step size is same as that of the previous case, but this time instead of occupying the middle position, the rotor is occupying a position which is parallel to the stator. Now there is another pattern which is called the half-step sequence, which is obtained by interleaving the normal 4-step sequence with the wave drive sequence. The effect is that first the rotor will be aligned parallel to the stator, then it will occupy a position in between 2 stators. Again, it will be aligned parallel to the next stator. Next, it will occupy a position in between 2 stators and so on. So in this case, it is rotating at half step. That is, suppose the angle, step angle was 2 degree. In the previous 2 cases, it will turn 2 degrees in a step. In this case, the half step sequence, it will turn 1 degree. It will only move half a step when this sequence is given. That is, when you interleave the normal 4-step sequence and wave drive sequence, the rotor will turn half a step. So in our programming, we are going to make use of the normal 4-step sequence in which 2 stators are energized at a time. So let's move on to the program. Now let's consider a program. This is the program to turn the stepper motor clockwise continuously. We are required to turn a stepper motor continuously. So if you look at the pattern that we used to energize our stators, it is as shown in this table. See, you can see that it is 6, 3, 9, 12 and repeat 6, 3, 9 and 12. This is the sequence which we should give when we have to rotate the stepper motor clockwise. So if you look at this pattern, you can see that you just look at the 4-bit pattern, the one shown in white. See, you can see that if you rotate the content or the first sequence by one position, you will get the second sequence. See, if you rotate 6 by 1 bit, you will get 3. If you rotate 3 once more, you will get 9. If you rotate 9 right, you will get 12. And if you rotate 12 right, you will again get 3. And if you continue in this fashion, you can get all the sequences in the required order, the order in which you need to send the sequence so that the motor turns clockwise. So what should we do? We should get an initial sequence and rotate it right. If you rotate it right, once you will get the next sequence. If you rotate again, you will get the next sequence and so on. So we will be inclined to use the rotate right instruction, but there is one problem with that instruction. It can be used only for the accumulator, and the another problem is that it is not a 4-bit rotate instruction. This rotate instruction is for an 8-bit pattern. So what can be done so that we can use the rotate right instruction? We will take a duplicate of this pattern in the other nibble also. So the upper nibble and the lower nibble, they are both containing the same values. The upper nibble is 6 and the lower nibble is also 6. Now if you rotate right, you can see that if you use the instruction rotate right the accumulator, you can see that the next sequence is obtained in both nibbles. 6 has become 3 here, 6 has become 3 here. Again, the next time you give the instruction rotate right accumulator, it will again rotate and you will get 9 in the upper nibble and 9 in the lower nibble also. So there is duplication of the pattern, but this instruction can be used, and the effect is that with this instruction you can continuously obtain the sequence for clockwise rotation. So from this 8-bit value, we will take a single nibble, a 4-bit pattern, and apply it to the ULN 2003 IC, and through the ULN we will apply it to the stepper motor. We require only 4 bits, but since we need to use the rotate right instruction, we are using an 8-bit pattern where the upper nibble and lower nibble are duplicates. So if we give the upper nibble equal to lower nibble and apply the rotate right instruction, we will get the required pattern in both the upper nibble and the lower nibble. We can use the upper nibble or lower nibble to be applied to the stepper motor through the ULN 2003 IC. Now let's look at the program. So I hope you have understood the logic. The logic is that if we rotate our pattern right, we will get the next sequence. So we need to use the rotate right instruction, and it can be applied only for the accumulator, and the accumulator is 8-bit. Since the accumulator is 8-bit, we need an 8-bit pattern. So we will use duplicate in the lower nibble and the upper nibble. Suppose we are starting with the sequence 6, then we will store 6 in the upper nibble and the lower nibble. So the pattern that we load into the accumulator will be 6, 6. So let us now look at the program. Now the first step is that we will load 6, 6 hexadecimal into the accumulator. Move a comma hash 6, 6 h. So this pattern will be loaded into the accumulator. Now we are assuming that our stepper motor is connected to port 1. Either the upper nibble of port 1 or the lower nibble of port 1 can be used, but in the correct order. So that if you are using the upper nibble of port 1, then you should connect P1.7, P1.6, P1.5 and P1.4 in the order to the ULNIC. If you are using the lower nibble, then you should connect P1.3, P1.2, P1.1, P1.0 should be connected to the ULNIC. You can use either the upper nibble or the lower nibble to be connected to ULNIC. So we will load this value into the port, and one of the nibbles, let's say the lower nibble. Now the lower nibble of port 1 is connected to the ULNIC, so it will get the pattern 0100110. Now you will rotate the accumulator once. Rotate right accumulator. Now the pattern in the accumulator becomes 0011. Once you rotate it right, the pattern becomes 0011. That is, the previous sequence was 6, now it becomes 3. Now we will call a delay. This delay is required because the stepper motor will take some time to turn. If we give the sequence continuously without the delay, the stepper motor may not be able to respond to it. So we will not get the pattern as we intend, and the motor is not going to turn as we intend. So the required delay has to be given. We need not use the timer for generating this delay, since a small delay will be enough, and we will be using a software delay, and the delay is given as a subroutine. So after rotating the accumulator right, we will call the delay, a call delay, that will provide a small delay. Then what should we do? We have now created the new sequence, and that is available in the accumulator. So 3 is now available in the accumulator. It should be sent to port 1. So we will jump to back. Back is the label of the instruction where we copy the contents of the accumulator into port 1. So 3 will now be sent to port 1 and through port 1 to the motor. So 6 came first, followed by 3. Now the rotor will turn clockwise by a single step angle. Now once 3 has been sent to the motor, we will rotate the accumulator right again, and now the pattern in the accumulator will become 9, 1001, 1001. And again we will call delay so that the motor gets time to respond, and after that we will repeat the steps. We will jump to back. So now the new pattern is in the accumulator. It will now be sent to port 1, and now the rotor will turn again by another step angle, and this process continues. This is continuous rotation of the stepper motor in clockwise direction. Now let's look at the delay subroutine. This is a simple software delay. We make use of the DJNZ instruction to generate this delay. Let's look at the first step. You are loading the value 100 decimal into R2. Then you load the value 255 decimal into R3. And DJNZ R3, H2. H2 is the label of the same instruction. So R3 will be decremented once. Now its content will become 254. It is not 0, so you will go to H2. Again it will be decremented. It will become 253. It is not 0, go to H2. Like this instruction DJNZ R3 will be repeated 255 times. And after that the content of R3 will become 0. Now we will decrement R2. So R2 was 100, now it becomes 99. And after decrementing we will go to H1 where we reload the count 255 into R3. Now R3 becomes 255. Again DJNZ R3, its content becomes 254. Non-zero, again loop here. This will continue again 255 times. And once this instruction DJNZ R3 has been executed 255 times, we will come to DJNZ R2. Now its content will become 98. That is also not 0. So we will go to H1 where we will reload 255 into R3. So what are we doing? We are executing the instruction DJNZ R3 255 into 100 times. This instruction will be executed 255 into 100 times. So that will provide sufficient delay for the stepper motor to respond to the sequence, and we will get a clockwise rotation, clockwise continuous rotation of the stepper motor. The important point to be noted here is that in our sequence, this is the sequence that we are going to use. In this sequence, if we start with 6, the next value that we should give is 3. After 3 we should give 9. After that you should give 12. Then 6. Then 3. This is the pattern that should be sent to the stepper motor through ULNIC. So if we start with 6, the next pattern is 3. And if after 3 it should be 9, after 9 it should be 12. To get this pattern, we just have to shift this pattern by one position. So to get the next sequence, next element in the sequence, you just have to rotate the sequence once right. You have to rotate right. But since the rotate instruction is applicable for the accumulator and the size of the accumulator is 8-bit, we need to keep a duplicate in the upper and lower nibble, and then we can apply the rotate right instruction, and we will get the pattern twice. We will get the pattern in the upper nibble as well as in the lower nibble. Only one nibble need be connected to the stepper motor. So when you load the accumulator content into port 1, and either the upper nibble or the lower nibble, any one of them of port 1 should be connected to the stepper motor through the ULNIC. That is the only thing that you have to understand. I hope you understood the program. Please read through the program. Please watch the video several times until you understand. And if you have any doubts, call me. We will discuss this in the next class, but after you have seen the video. So all of you should see the video so that we can discuss the doubts in the live class. Thank you.